So it's my pleasure to welcome Nicolas Schunck, who will tell us about the theory of nuclear fission.
All right, thank you very much. I'm very happy to be here. I wish I had been present physically, but that's what it is. So the goal of this presentation is to give you an overview and kind of introduction to a modern theory of nuclear fission. And I will try to explain so why in 2021 we are still talking about nuclear fission, even though the process was discovered almost 80 years ago now. So before we start, I thought perhaps I should just remind you a few things about nuclear physics, nuclear science. So nuclear physics is a branch of physics that studies the properties, reactions, and structure of atomic nuclei. I don't think I need to remind this audience that matter is made of molecules, that those molecules are made of atoms. The atom itself is made of a central nucleus surrounded by a cloud of electrons. And then nuclear physics is basically the branch of physics that studies everything that is nuclear or subnuclear in scale. So in this slide, I also put some typical energy scales and length scales to put things in perspective. The atom has typically about 1 electron volt. That's the usual energy scale. The length scale is about 1 angstrom or 10 to the power minus 10 meters. Now, in a nucleus, the nucleus is a lot smaller than the atom. The typical length scale is 1 femtometer or 1 Fermi, but it packs in a lot more energy because the typical energy scale is about 1 mega electron volt. Now, if we get to the structure of nucleons, that is protons and neutrons, and how nucleons are formed of quarks and gluons, things get weirder because then the length scale is not that much smaller than the nucleus itself, and that's an illustration of quantum mechanics in action. So now, I think it's always useful to have a few, to go back in history and remember where everything came from. So there is a sort of agreement that the birth date of nuclear physics is in 1932 when Chadwick discovered the neutron, because that means that at the time they had the basic ingredients of the nucleus. They knew that it was made of protons that give it its charge, and they also knew that it was made of neutrons that contribute to its mass. And from 1932 onwards, there was about 2 to 3 decades of golden age for nuclear theory, for nuclear physics in general. In 1935, there was the first quantitative model of the nucleus, the Bethe-Weizsäcker mass formula. 1939 was the discovery of fission. In 1949, the discovery of the sham model and how the quantum nature of the nucleus impact its properties. By the late 1950s, people discovered that nuclei could be superfluid, and that discovery was made almost at the same time as the one in condensed matter. And then by the late 60s, the physicists were digging deeper and deeper into the structure of the nucleons, and in particular, the quark structure of the protons and the neutrons, and this sort of forked out to the standard model of particles. So, broadly speaking, nuclear physics falls into 2 main categories: the physics of hadrons and quarks and gluons that are described by quantum chromodynamics or QCD. QCD is one of the pillars of the standard model of particles. It's also a typical example of a relativistic quantum field theory. In this presentation, I will focus instead more on the physics of nuclei, which takes place at much lower energy scales of the order of the MeV, and where we treat protons and neutrons as point-like particles. So we completely ignore their subnucleonic degrees of freedom. And we also don't use relativistic quantum field theory. We tend to use quantum mechanics, of course, of many body systems, but that is still simpler than relativistic quantum field theory. Typically, there are lots of elements. There are a lot of atomic nuclei in the universe. It's customary to put properties of nuclei on a chart like this. This is called a chart of isotope or nuclear chart. So you put things as a function of the number of protons in the nucleus, which, as I say, give the nucleus its charge, and the number of neutrons that determine the isotope of the element. So the black squares here are the stable isotopes, which means the one that you can find around us in nature. The green, the red, and blue ones are unstable isotopes that have been studied in the laboratory nuclear reaction experiments. And there is about 2,000 to 3,000 of them. I don't remember the exact number now. Now, what is more interesting is the yellow area. These are the unstable isotopes that we think could exist, but we are not sure because we've not seen them yet. And we don't exactly know how far we can go on that side here, on that neutron-rich side. How many neutrons can we really put into a nucleus before it becomes really truly unstable? We also don't really know the limit of stability towards heavier and heavier elements. And these are some of the open problems in basic nuclear science, is to try to predict those limits. And this has impact beyond nuclear science. This has impact in chemistry because, well, the heaviest element that has been observed is oganesson, which has 118 protons. The question on not whether this table of elements ends right here or whether it can be extended depends in part on the structure of the nucleus of those elements. If the nucleus is unstable, there is no chance you can make an atom with them. So this is just to sort of highlight that nuclear science has impact on other disciplines, in particular chemistry, but also in astrophysics. Nuclear fusion reactions between light ions are the fuel that power of stars, like the sun. So if you want to model the sun, you have to know a lot about the basic nuclear physics. And this weird-looking picture here is a simulation of a neutron star merger. And today there is a lot of indications that in fact these kind of galactic events is where most of the heavy elements, so heavy elements means everything heavier than lead, will be produced in the universe. So there's a lot of suggestion that these neutron star mergers would be the key mechanism where those elements are produced. And if you want to simulate those mergers, of course you need astrophysics, but you also need to know a lot. You need to know, in fact, all the data that you have about every nucleus in the nuclear chart. So this was a very short introduction just to highlight, sort of give the big picture, the context in which what I'm going to discuss next takes place, which is fission. So as I said, fission was discovered experimentally in 1939 by a team of German physicists. What they found is that they were playing with bombarding uranium isotopes with neutrons. And what they observed is that they were creating isotopes of barium, which is much lighter, just 56 protons. And at the time, they couldn't understand what exactly was going on. And this is Lise Meitner, picture here, who understood and explained qualitatively what was happening. And she realized that what was happening was that, in fact, the uranium nuclei were dividing into smaller systems. And she explained it with the theoretical model of the time, which was the leaky drop model. If you bring in energy to a leaky drop, it starts agitating. And if it agitates enough, it becomes unstable and can divide into two smaller drops. So this was neutron-induced fission because the mechanism that triggered fission was the bombardment of those nuclei with neutrons. But in 1940, Russian physicists discovered that, in fact, if you let some heavy nuclei just by themselves, they would also undergo fission spontaneously without any external mechanism. And so this was the discovery of spontaneous fission. So all of this is very old. And as I said, as I was teasing in my introduction to the talk, you may really wonder why we're still talking about it. I'm sure you know that there are such a thing as nuclear reactors and nuclear weapons. So you would think that we know about fission, but the truth is that most of that knowledge comes from experimental measurements and from models that are very phenomenological and that are calibrated heavily on those same experimental measurements. So what we don't really have is a predictive theory of the phenomenon, where you would just start from basic principles, make calculations, and those calculations would actually be correct. So this is needed for understanding the structure of superheavy elements, as I was briefly mentioning, to understand how heavy elements are formed in nucleosynthesis. But in practical applications, to model the fuel cycle of a nuclear reactor, you also need such a predictive theory of fission. The problems are that it's not that easy to get data because some of those isotopes that you may be interested in are unstable, so their lifetime is too short to make the experiment. Sometimes it's too expensive. Sometimes it's kind of dangerous because it's radioactive. And so you don't have that much data to validate, with which you could validate your models. The second problem is that in your models, small variations of the ingredients of the model could lead to very large variations of the output. And this can be somewhat understood from this picture on the right. What I'm showing here is the spontaneous fission half-life of heavy elements. The scale here, this is a log scale. The half-life is marked in years, so the half-life is just the time it takes for half a sample to undergo fission. And this is shown as function of this weird unit here. The takeaway here is that there are 35 orders of magnitude in between the longest lived element and the shortest lived one. And for any model in any branch of science, that means that you will have huge uncertainties in your predictions because of this broad range of outputs. In nuclear physics, fission involves atomic nuclei. We are dealing with two major problems. One is that this is the atomic nucleus is an example of a quantum many-body problem, where you have several constituents that are strongly interacting and at the same time obey the laws of quantum mechanics. And there is no exact solution to that problem. So you have to come up with models. But the difficulty is that we don't even know what the nuclear forces between protons and neutrons are. We know that they are derived from QCD, but they are not nuclear forces are not one of the four elementary forces of nature. They are effective forces, and that adds some difficulties in the description of the phenomenon. So what exactly now is fission? Let's try to discuss it in more details. There is a one-sentence description of it, which perhaps is a mouthful. This is a large-scale collective motion of a strongly interacting quantum many-body system without S. And what it is in practice is we still think of fission pretty much as Lisa Meitner was thinking about it 8 years ago, namely as a deformation process. So for some reason, either spontaneously or because of some external probe, the heavy atomic nucleus will start deforming itself, and it will deform itself so much that it splits into two fragments. Now, the first thing to realize is that those fragments are not identical. In fact, if you have a sample of radioactive material that undergo fission, you will not always get the same fragments. You will get a whole distribution of them. And so this figure here is a calculation, but it's a good calculation. And it shows the probability of forming a certain fragment with a charge here. So this is the number of protons and a total number of particles or mass on the x-axis. And you got dozens of fission fragments that are formed in the fission of, let's say, I think for this figure, this was uranium-236. Okay, so you have lots of fission fragments that are formed with different probabilities. Now, this is not the end of the process. It's actually just the beginning in a way. All those fragments are excited, and they will de-excite first by emitting neutrons. And when they run out of energy to kick out neutrons, they will emit gamma rays or photons. And this phase of the process is called the prompt fission spectrum because it takes place very fast. After a while, first of all, after this, at the end of this prompt fission, of this prompt emission, you have changed the isotopic content of your fission fragments because of the neutron emission. But some of the fragments may still be unstable against beta decay, by which you will turn a neutron into a proton and release an antineutrino and an electron. And so this will stabilize the fragments. So the fragments may undergo one or several beta decays before finally everything settles down and we can say the process is over. At the end of that whole process, you have a lot of what we call fission products. You have emitted a lot of particles, neutrons and gammas and antineutrinos and electrons, and some of them are very energetic. And all of this, if you look at the time scale at the bottom, happened very fast. The typical time of scission is of the order of 10 to the power minus 20 seconds. This is extremely fast. And then, of course, the decay depends on the particles and all this. The point is that you can make measurements of some of those emitted particles, depending on how fast it takes place. But there is no way you can measure things that are related to this part of the process, the initial conditions with which the fragments are formed. And that's where there has been a lot of progress, is trying to simulate that with as fundamental a theory as possible. And that's what I want to discuss in this presentation. So what are the two main basic concepts of fission? So this fission is really a quantum mechanical system. So you have to follow the laws of quantum mechanics. That is, you can think of it as that system moves through a potential energy surface. And so I was told that everybody has done I've studied the Schrödinger equation. And so if you study the Schrödinger equation, you have played with potential wells. So here is an example of a potential well. Potential energy as a function now of some deformation of the nucleus. So it's not X, Y, or Z, it's deformation of the nucleus. So you have a potential well like this. The deepest well would correspond to the ground state of the nucleus. In most of the actinides, so uranium isotope, plutonium isotope, thorium, and so on, you typically have a second minimum, which is called the fission isomer. And then there are barriers separating the ground state from the fission isomer, and then the fission isomer from the rest. The point where, so the nucleus deforms so much that at some point it will snap into two fragments. So the first important concept is that because this is quantum mechanics, the probability of fission will be related both to the height and the width of those barriers, but also to the initial energy of the system. For spontaneous fission, the system is in the ground state, so deep inside the well. For induced fission, the system may have a much higher energy. And this is the first important concept in fission. This is the fact that the probability of the process taking place is related to the underlying potential energy surface. That doesn't explain, however, why you don't always get the same fragments. In order to understand this, you need to realize that it's not a one-dimensional potential energy curve, but it's in fact a multi-dimensional potential energy surface. So this is an example here where what I plotted is the same potential energy. The difference between this one and that one is that the one on the right is actually a calculation. The one on the left is just a sketch that I made for pedagogical reasons. So you plot here, what I plot here is the potential energy as a function of two different deformation parameters, one that correspond to the elongation of the nuclear shape, so how far the shape stretches in a certain direction. And the second one is represents the left-right asymmetry of the shape. So whether you have a big blob and a small blob, or whether you have kind of symmetry around the middle. Now, if you have a shape with no asymmetry, what that means is that when the system, if a shape like this splits in two, the two fragments will be identical, which means they will have the same number of particles. Conversely, if you have a shape with a large asymmetry, this means you will end up with a much bigger fragment and a big fragment and a small fragment. The number of particles will be different. So you will have a heavy and a light fragment. And so this is the second important concept, is that the number of particles in the fragments can be in fact mapped to the deformation of the nuclear shape. And this is very useful to come up with predictions as to what kind of fission fragments should be produced. Okay, so this is good, but this is still qualitative. How do you, in practice, how do you calculate such a potential energy surface? You need a theory. And the theory we use is called density functional theory. I'm pretty sure that many of you are familiar with it. It's a general approach to remap the quantum many-body problem. It's used in electronic structure theory, in molecular physics, in quantum chemistry, and in nuclear physics. The basic ingredient is some knowledge of the forces that take place in the system. So in a nucleus, nuclear forces. So I try to represent here the most important part of the nuclear force, which is the central part of the force. And this is for the two-body piece of the interaction. So what we know of nuclear forces is that at long distance, they vanish. At short distance, they become infinitely repulsive. So this is what we call the hardcore. And then there is this sweet spot around 1 Fermi or 1 femtometer, where the nuclear forces are maximally attractive. Now, this is just for the two-body part of the nuclear force, because contrary to, for example, the Coulomb force or gravity, nuclear forces are many-body forces by construction. So this means they involve simultaneously 2, 3, 4, 5 A-body nucleons at the same time. This is different from many-body effects that are induced. This is in a way, the force itself is not just two-body, but many-body. So this means that when you try to calculate the properties of the nucleus, it's incredibly complicated, because you have these dozens of nucleons that are all interacting 2 by 2, 3 by 3, 4 by 4, A by A. And so it's intractable, except for the very lightest nuclei. So what DFT does, it replaces it by describing the system as A particles that are independent of one another. So you replace A particles in interaction with A independent particles you only have to specify that those particles move in a common potential. This is what is known as independent particle model. And if you think that's kind of a drastic approximation, it's actually very well justified in nuclear physics because of the very long mean-free path of nucleons inside the nucleus. If you try to measure it, you find that the mean-free path is practically the same size of the whole nucleus. So everything happens as if nucleons were really independent of one another. And qualitatively, that justifies this mean field, what we call mean field approximation, that underpins the nuclear DFT. So again, that's kind of qualitative. So now I'm going to start showing some equations. How do you solve nuclear DFT in practice? Again, I assume you all know about the Schrödinger equation. In case you don't remember, I put it there. This is a differential equation that involves the Laplacian here, some potential that is dependent on the problem you want to solve. But this is also a linear eigenvalue problem because solving this equation means finding the eigenvectors, the wave functions, and the eigenvalues, the energies of your particle of mass m. Okay, so in quantum mechanics 101, when you learn about it, typically you take some very simple forms of V, like V equals 0, or V is a constant, a square well, a harmonic oscillator, or something like this, and you try to solve that equation analytically. The sort of core equation of DFT is the Kohn-Sham equation that looks pretty similar. It's written here at the top, I mean, right there where my mouse is. The difference is that the potential now depends on the density of particles, in that this density of particles is the sum of the square of the wave functions. And what that means is it's not a linear eigenvalue problem anymore. It's a nonlinear one. The potential that defines the operator depends on the solutions, which means you need an iterative procedure to determine those solutions. And typically what people do is they take a guess for the potential. For example, you could kick in this, you could initialize this iteration anywhere, but if you can take a guess for the potential, in which case you define this operator completely. You can then solve the Schrödinger equation. You get a new set of wave functions. From those wave functions, you can recalculate the density. This gives you a new version, a new iteration of the potential, and then you can rediagonalize it and keep going until nothing changes anymore. So this self-consistent mean field theory is a staple of many different, it's a standard tool of many branches in subatomic physics. It's used in nuclear physics, atomic physics, molecular physics. Archifock is kind of what I presented here. They are extensions. In fact, in nuclear physics, we use mostly the extensions, but I don't want to get into too many technical details. Okay, so we know that we want to calculate potential for fission. We want to calculate potential energy surfaces. We know that we have to solve the Kohn-Sham equation for this. But how do we introduce deformation then? How do we describe deformed nuclei, including deformation corresponding to two fragments that are separated within DFT? And the answer is you can introduce constraints. So imagine that you have a shape like this. This corresponds, in fact, to this would be the representation of the density of the density volume. So now you can try to characterize that shape by some parameters corresponding, for example, to its elongation, to its left-right asymmetry. In this particular example, there is none. To the size of this neck here between the two objects. And so you could add constraints on the value of those parameters. So you add constraints, in fact, on the density, but indirectly via some of the shape parameters. In the case of fission, you will need at least two such parameters, one that will correspond to the elongation, because this is what basically drives fission and lead the system to split, but also another one corresponding to the mass asymmetry to understand that you have also a heavy and a light fragment in many cases. And in fact, you need probably between 2 and 5 deformation parameters. So once you have those deformation parameters, you can solve the Kohn-Sham equation with constraints, and this will give you the solution for the nucleus that is deformed. I don't really have time to take too much about it, but I want to highlight that this is formally, this is an example of what is known as spontaneous symmetry breaking, which is a cornerstone of modern physics. If the nucleus is deformed, then the symmetries of the nuclear Hamiltonian are actually broken, and this happens spontaneously. And this is extremely important in quantum physics So it kind of gives a formal justification of why we can think of fission as a deformation process. Again, you can ask me questions later, but this is a little bit technical. Now, if you remember the two-dimensional potential energy surface that I showed, there were about 10,000 points in them. So that means I had to solve the Schunck equation 10,000 different times for 10,000 different set of deformations. And you can think of, on average, it took about 3 hours on 4 cores to solve the Schunck equation for a single deformation. Okay, so if you have 10,000 deformations, you need to multiply 10,000 by 3. And if you do the math, then you find that if you only have a standard desktop, it will take 3.5 years to run on that desktop, which will become pretty useless then. On the other hand, if you have access to supercomputers, supercomputers that are big enough, then you can still run the calculation in a few hours because all those calculations can be done independently of one another. So what I just want to highlight here is that fission theory, modern fission theory based on density functional theory, involves a tremendous amount of computing. This also means that we have to deal with software development problems. We are using a lot of shared and distributed parallelism. We are working with GPUs because the architectures of the supercomputers uses more and more GPUs. So at Livermore, we are lucky to have some of the biggest computers on the planet. Some of them are shown here. On the left is a computer called Ruby that has about 90,000 cores, I believe, and it's just an Intel machine. And here in the middle is a supercomputer called Sierra, which I believe has 1.5 million cores and is an IBM machine. And fission theory is always happy to get computers of that size because we need them, okay? All right, so you can calculate, we've seen that we need a potential energy surface, a multidimensional one, to understand the physics of fission. I try to show you briefly that in order to get that surface, you need to solve the Schunck equation with constraints. And all right, fine. At that point, if you have the potential energy surface, you only know what fragments you can populate, but it doesn't tell you what's the probability of populating them. In order to get that, you have to compute the flow of probability in that deformation space. This is what will give you access to the fission fragment distributions that you can then compare with experimental data. So how do you do this? You use a basic principle of quantum mechanics, which is a superposition principle. You start from an ansatz for the time-dependent wave function of the whole nucleus, and you will write it as a sum of different shapes with weights that are time-dependent functions, and these are the functions you want to determine. And those shapes correspond to the shape that you have pre-calculated in your potential energy surface. And then, of course, I'm trying to simplify things a little bit. You can imagine that it's not a discrete sum. This is going to be an integral. It's going to be not necessarily one-dimensional. It's going to be a lot more complicated, but you get the idea. Now, I spare you some of the math. If you plug this ansatz into the many-body time-dependent Schrödinger equation, you can obtain a diffusion-like equation that gives you the probability to be at a certain deformation q. Generically, I would call those deformations q. It's a vector at time t. This equation looks like that. That's the last one I'm showing, I think. So it looks a bit like a time-dependent Schrödinger equation. You are taking the time derivative on the left. There is an operator here that looks a little bit like the Hamiltonian. There is a potential energy. And then there is this guy, which is equivalent to the kinetic energy, except it's not in the usual Cartesian space. It's in the deformation space. And then there is this object B, which is called the collective inertia, which kind of gives you the resistance of the motion through the deformation space. The good news, however, is that when you calculate the potential energy surface, you get those two objects in green directly out of it. So if you know those two objects, you know this operator, and you can solve this equation. And solving it will give you this function g, which is the probability amplitude to be at a certain deformation at time t. And from that function, from that probability amplitude, you can calculate a flux of probability. And from there, you can extract fission fragment distributions. So I'm going to show you a movie where this is happening. So this is a visualization of the flow of probability of this collective wave packet across a potential energy surface for the particular case of plutonium-240. So you have a 2D surface, which is characterized by an elongation parameter here and an asymmetry parameter on which is called Q3. This red line here is what we call the scission line. So this is what separates in that surface the geometries where the system has not split from the ones where it has split into two fragments. And then this color-coded contour maps is the actual probability to be at a certain point on that surface. Now the evolution stops. I didn't make it run all the way to the end, but if I did, at some point all that wave packet would cross the Fission line, and from the flux of that crossing you could extract the Fission fragment distribution. And here are some examples of how well it works. It's not too bad for nuclear physics standards. So roughly speaking, 20% agreement with experiment. I show you 3 different examples, 2 in actinide, so uranium-236 and plutonium-240. This figure shows the charge distribution, so the probability of having a certain number of protons in the fragments. And then at the bottom, this is the mass distribution, so the probability of having a total number of particles in the fragment. Both systems have what we call asymmetric fission, so there is a light and a heavy fragment, and so this is why those 2 peaks are actually completely symmetrical. You have this is the peak for the light fragment, and this is, if you have the light fragment, then you have the complementary heavy one. So if you wanted to compare theory with experiments, you should look at the red curve here and the orange one. So these are the theory, P and B, and then the symbols are the experimental data sets. I'm sorry, we put the paper on the archive yesterday, so I don't have the ID number yet, but tomorrow it should be online. If you look it up, it'll be there. I show here another example which shows the predictive power of such an approach. This is to look at fission in fermium isotopes. What's interesting there is that fermium-254 has fission in an asymmetric way. So there is again a light and a heavy fragment. But then in fermium-258, which is just 4 more neutrons, fission is completely different. It's mostly symmetric. So mostly the 2 fragments are identical. And the theory calculation in red can reproduce at least semi-quantitatively this result. So this is a good test, a good validation of the theory. Now, these fission fragment distributions are just the beginning. DFT, in fact, can give you a whole wealth of information about those fission fragments. And if you remember the initial, this kind of sketch of the whole process that I showed at the beginning, if you want to simulate the decay of the fragments, the emission of neutrons, the emission of gammas, the beta decays, you need to have a complete characterization of the fission fragments just at the point of scission. That is, what are their proton and neutron number? What is the excitation energy? What is the spin of those fragments? What are the level densities? And none of these quantities is measurable experimentally. So you really rely on theoretical calculations. And DFT gives you a framework to compute a lot of these guys in a consistent manner. So what I show here is 2 very recent examples, again, submitted actually for publication just a few weeks ago, or even yesterday. One is the calculation of a sort of better estimates of the number of particles in the fragment for 9 different shapes of the nucleus at scission. We are now calculating the dispersion in particle number for each of these shapes. So this gives you a more refined estimate of how many particles really are in the fragment. And then on the right is an application of similar techniques to calculate the spin of the fission fragment. In fact, each fragment has an average spin, but it has also a spin distribution. And we can use DFT methods, a particular extension of them called projection techniques, to extract this information and feed that information to the codes that will de-excite the fragments. Now, these days, you cannot give any presentation on anything without talking about machine learning. And well, funny enough, actually, it is very relevant for fission theory. For 2 reasons, mostly. One is that whenever you have a model, a nuclear physics model, it always depends on some parameters. And that is true for every nuclear theory that is on the market. There are parameters. And if there are parameters, they are not given by the theory itself. They need to be fitted, they need to be calibrated on some data. And the question you may ask is, okay, well, this calibration will lead to some uncertainty in the determination of these parameters. And you may wonder how those uncertainties propagate all the way to these fission predictions. So what I show here is a little old example now from a work of a few years ago, where we try to use a technique known as Gaussian processes to estimate the uncertainties on fission barriers for plutonium-240, the uncertainties caused by the uncertainty of the parameters of the energy functional. And so this is just an example of this kind of, this is part of machine learning, broadly speaking. Another example where machine learning is useful or is considered as potentially very useful is a calculation of potential energy surfaces. They can be very expensive computationally, as I tried to indicate. If it's two-dimensional, it's still okay, but if you're thinking of 3, 4, 5-dimensional potential energy surfaces, even the biggest computers that you can have will not be enough. So the question is, can we build emulators of our DFT models and use the emulators to generate the results? So this is an example of supervised learning where you have, so I'm trying to illustrate a little bit what it gives here. So suppose you have a potential energy surface like this. This is a 2D representation, a contour map. The black dots are the ones that I calculated. And then I'm going to select a few of them, which I have not calculated. And I'm going to try to build an emulator of my DFT model to predict what the value of the energy and other quantities could be at those points. So what I show here is a comparison between a particular component of the nuclear mean fields, as it should be. This is the actual calculation, compared with the result obtained with the emulator, which uses Gaussian processes if you're interested in the details. So this is something that is being explored more and more, is to alleviate the computational cost of some of these calculations by using machine learning and artificial intelligence techniques. Okay, so I'm just going to conclude. Briefly, so nuclear fission is old. This is more than 80 years old. And yet we still are trying to build a predictive theory of that process. I'm trying to highlight that density functional theory is, in fact, provides a practical, fully quantum mechanical framework to describe it, where fission emerges naturally from nuclear forces and many body effects, where the number of free parameters that you need to adjust on data is actually limited, and where the computational cost is high, but still manageable. And with machine learning tools and with bigger computers, it may become easier and easier. And then I try to take my to try to play at forecasting the future, identifying what the future trends in the field could be, and I listed 3 of them. There's been more and more work on incorporating basic tools of nuclear theory into fission models. This has been enabled by advances in computing, and I think that trend will continue because it provides a much more predictive and consistent framework. Definitely we'll hear more and more about large-scale fission calculations for example, applications like astrophysics. And then for applications, which is a code word for nuclear reactors and other things, you need to continue this work on trying to determine the initial conditions of the fission fragments. And this is something also that DFT is a good candidate to do. And on this note, I am done, more or less on time.
Thank you very much. Round of applause. Okay.
Virtual.
Okay, so questions. We have a couple. Let me go to the ones that were in the chat, and then anyone else can just raise their hand and we'll go through. So Jose, would you like to just ask a question? Are you here? Okay, so I'll just read it off. So the question is, in your description of the characteristics of fission and the landscape that you pose, what are the conditions under which that is sort of the thermodynamic conditions, like 0 temperature, pressure?
Oh, yeah. This is which figure exactly you refer to?
The landscape.
The landscape. This particular potential energy surface was calculated at 0 temperature. Density functional theory there is an extension of it that can deal with finite temperature, although the very concept of nuclear temperature is a little ambiguous because it's not like this system is put in some thermostat somewhere. So the temperature, in fact, comes from the intrinsic motion of the nucleons. But anyway, there is an extension of DFT at finite temperature. I have examples of such surfaces. There are also other ways to deal with the excitation energy, because this question is actually related to the excitation energy of the system, and there are more direct way to do it since everything is at relatively low energy. So we can track down excitations directly rather than using temperature. And the example I showed, it was 0 temperature.
Okay, and then Guy Worthy asks a question about whether or not quantum computing is likely to ease the computational requirements for ab initio fission calculations.
The answer is, I'm going to use a German word. It's going to be Jein. So it's a combination of yes and no. And Yes, in the long term. Yes, in the long term, because in fact, so fission is a time-dependent process, and in principle, quantum computing is particularly adapted to dealing with unitary evolutions of a quantum mechanical system. So you could imagine being able to map your fission problem into it is actually a form of time evolution, and to map it onto a quantum computer. However, that is not going to come anytime soon, certainly not in my lifetime, and I'm not that old yet. So that's my personal interpretation. I mean, some of my colleagues at Livermore in our group actually work on quantum computers. They may disagree, but that's my answer.
Of course, we already have quantum computers that do this. They're called nuclei, and the quantum. But that's a very.
But it is one of the motivations to build quantum computers is to try to solve problems, because it's true that the computational cost of those simulations are really, really large, and so at some point, it also becomes a question of how much precision do you want to achieve, and are you happy with the precision you have? If you need always more precision, then you need bigger computers, and quantum computers can be part of the equation. But this is for a relatively far future.
But then there is the real question: even if you had a perfect quantum computer right now, a digital quantum computer, is the theory that you're putting on it? I mean, how well do you know
it's not.
that?
Yes, no, it's not exact. Yeah.
So then this is the Okay, Ryan has a question, and then Robbie.
You might have gone over this, but how do you determine the scission line?
That's you're opening Pandora's box. This is so they are. I did not detail it at all. I didn't discuss it because this is a kind of worms. So what I was presenting was a description of fission, which relies on kind of a two-step process where you first explore the deformation properties of the nucleus, and then on top of that, you do some time-dependent evolution to get probabilities. The problem with this approach is that when you calculate the potential energy surface, you minimize the energy. And if you minimize the energy for a shape that corresponds to two fragments that are separated, what you will find is that the two fragments are in their ground state, because that's what minimizes the energy. And unfortunately, that's completely unphysical, because in nature, when the fragments are formed, they are excited. So what that means is that we cannot wait until, or we cannot calculate scission when the fragments are really separated. We have to do it before they are separated in that particular approach, which becomes ambiguous. You have to come up with a criterion of when exactly are you going to stop the calculation in a way. So in the calculations I showed, we use a criterion based on the number of particles in a neck between the two pre-fragments, but this is ambiguous. Now there's another way of dealing with fission, which is time-dependent DFT, where what you see, I didn't talk at all about it, but what you do is you simulate the time evolution of a single fission event. So you have the nucleus in initial state, and then you solve the time-dependent DFT equation, and you find that it starts deforming, and then it splits. In that approach, energy is conserved, and because energy is conserved, you can look at the fragments after they are separated. They're going to be excited in such that the total energy is conserved. So this is a much better way, except it only works for most likely fission. So you don't get, if you do TDDFT simulations of fission, you do not get some exotic fragmentations where you have a very light and a very heavy fragment or things like this. You only get always the most likely fission. So it is very useful, but it's not sufficient.
Okay.
And Robbie?
Yeah, so I have a question. So you're mentioning that you were solving the Schrodinger equation using like Hartree-Fock method. Is that correct?
That was a simplification of the truth, but yes.
But have you? I'm assuming that there have been many methods applied, and although like quantum Monte Carlo simulations aren't really good for time evolutions, but have those been implemented even for short scale?
Yes, so there are quantum Monte Carlo so there are people working on quantum Monte Carlo simulations of nuclear structure, in particular at Los Alamos and Argonne National Lab. The limitation of this approach is the number of particles that you can describe. So in practice, I don't know on top of my head, but I believe that I don't go much higher than oxygen 16 or system like this. And if you're interested in fission, you're interested in much, much heavier systems than that. So it's really actually, that's an example where perhaps quantum computers could be useful because it doesn't fit on a computer. So you cannot really apply these methods, and you won't be able to apply those methods anytime soon to problems like fission.
Gotcha. Thank you. Appreciate it.
Any other questions? All right. Hang on, I had a question. Do you see, or do you, I'm wondering about the role of like phenomena like measurement in quantum mechanics. So you have this picture where the nucleus is sort of splitting up into fragments, but it's really a superposition of all of those different states. But if there's any external fields or something, then that in principle could trigger some sort of measurement and sort of separating these two things and then putting this all into the DFT framework. I mean, this is one of the things I'm hoping that we can really try and study with the cold atom systems. But do you have any comments or?
Yes, I think this is so. We have been discussing with various people about whether or not we could study quantum entanglement in fission, because when the fragments separate, they are definitely entangled, but then very quickly they are flying apart from one another. And the question is, do we have a loss of coherence or not? And I asked, I'm not an expert in this field, so I asked around, and some people told me, of course, decoherence takes place immediately, blah, blah, blah. And others say, no, not at all. It stays entangled. In which case, if it's entangled, as you say, if you do something on one of the fragments, that should have a consequence on the other. I think that problem has not been really looked at rigorously, and it's a pity because it's a fascinating basic science problem. Fission this is an example of a quantum many-body problem that begets two quantum many-body systems, and so they are. I've looked a little bit in the literature. There are techniques to measure how much a system is entangled. I think it would be very cool to try to apply this to fission and see, and perhaps use cold atoms as proxies, simpler systems where things can be controlled a little more easily, to see whether indeed the system remains entangled or not. It seems to me from experimental data that probably is not entangled anymore, but it still needs to be addressed. I don't know if I answered your question, but I thought that was
sort of, yeah. We should talk more. Any other questions? I have one other one if no one else does. So you mentioned that you're currently, things are at sort of a 20% level of accuracy for some of these fragments. And what level do you need to be in order to be useful for quantum data, nuclear data needs? How
another very loaded question.
Yeah.
I think it depends very much on which application we have in mind. So astrophysics application, for example, 20% is good enough in the sense that at this time, there are so many other sources of uncertainties that for fission fragment, actually the 20% was about fission fragment distributions. There are other quantities related to fission, like the number of neutrons emitted, the number of photons emitted by the fragments, but also fission probabilities that are a lot more difficult to calculate, and where the uncertainties are probably much bigger. So for astrophysics, 20% precision on fission fragment distributions, that's great. For nuclear engineering applications, that is nowhere near enough. They need 1%, 0.1%. I mean, the precision needed for applications is out of this world. And this is in fact why in those fields, people doing nuclear reactors, people looking at non-proliferation applications, they don't use basic theoretical models. They use simple models that are heavily calibrated on data, because you don't want your reactor to explode. You want it to operate safely, and you want to make sure you don't make a mistake. So our theories or nuclear theories in general are not at the level of accuracy and precision where they can be used directly in applications. There is a lot of massaging that has to take place before they can be used.
But I also know that there's large swaths of nuclear data tables that are incomplete, and they need
Correct.
something.
And yes. So
yeah,
it's
and you need
that,
to
and
bring
that's
the
why.
theory together with the experiments, and yeah.
So that's why I was thinking, I was taking the example of astrophysics, where there are many nuclei where we will never make any measurements. And so having a theoretical calculation that is not too bad, it's great. I mean, this is all that we need. But for nuclear reactors and stuff like this, the nuclear data that we need is not on such very exotic systems. They are systems that can be measured for most of them. And so the room for error is a lot smaller there.
All right. If there's no other questions, then let's thank Nicolas once more for a very good talk.
Thank you.
Thanks, Guy. Thanks being with you.